Hello, everyone, and welcome to our Friday seminars, albeit online today. We are delighted to have with us today as our speaker, Dr. Purnamrita Sarkar from UT Austin. Unfortunately, she couldn't make it in person today, but at least we're lucky to have her available online. Purna is currently an associate professor at UT Austin at the Department of Statistics and Data Science, and she's also affiliated with the AI Institute and the Encore Institute, both of which are NSF-funded joint ventures among different universities. She received her PhD in machine learning from Carnegie Mellon University, and before that, her BTech in computer science and engineering from the Indian Institute of Technology. And before joining UT, she also completed a postdoc in statistics at UC Berkeley with Peter Bickel. Her general research interests lie at the intersection of asymptotic statistics, network models, and scalable algorithms. And more recently, she has also got interested in uncertainty quantification for streaming data models and also resampling-based inference for network models. And needless to say that she has done lots of high-quality work in all these areas over all these years that have appeared in top journals in both statistics as well as machine learning. And today she's going to tell us about some of her recent interesting work on bootstrap-based inference for Oja's algorithm for streaming PCA. So please join me in virtually welcoming Purnamrita. And Purna, please go ahead whenever you're ready.
Great. Let me share my screen, and thank you for that great introduction. Okay, can everyone see my screen?
Yes.
Okay. Hello, everyone. Thank you for being here. And it's really very nice of Jesus and Dr. Chakrabarty for inviting me. And I basically had, my son is sick and I am a little sick. And so I regret not being able to be there in person, but I'm very glad that I can at least do this online, and I thank Judith for that. So let me get started on the talk. So this is the title of the talk is Bootstrapping the Error of Oja's Algorithm. And, you know, in hindsight, maybe we should have named it Bootstrapping the Error of Streaming PCA, because that's the algorithm of Oja that we are talking about here. And I'll talk about that in more detail in a second. This is joint work with Robert Lundy, who was a former postdoctoral scholar. He's currently an assistant professor at the Washington University at St. Louis in the Mathematics and Statistics department. And also my very esteemed colleague, Rachel Ward, who is a professor in the math department in UT Austin. Okay, so let's get started. Here is a rough outline of my talk. And I also do want to say that while I know that on an online setting, it's hard to do clarification questions, please do stop me and ask questions, because that way I know that I'm making sense and hopefully it'll be fun. Okay, so here is an outline of my talk. We are going to talk about streaming PCA. The first several slides will basically be just background, motivation. Then I'll talk about distributional approximation, and finally I'll talk about online bootstrap. So that's kind of the high-level outline of this talk. Okay, so sorry. Okay, so let's talk about principal component analysis and optimization problem. This is such an important problem. We all have seen different versions of this. Here is a very simple setting. I have n data points. N is the number of data points. They are IID, mean zero random variables in d dimensions with common covariance matrix sigma. And our goal is to learn the principal eigenvector of sigma, right? And the way we write down the optimization program or optimization problem is you're trying to find a unit vector such that if I project down my data on that unit vector, the variance is maximized. And that's exactly what this optimization problem is doing. This objective function is doing. It's one of those objectives which are non-convex, but the surface is really nice. It doesn't have spurious local optima. So let me show you very quickly one example. Here is just easy to show, easy to visualize 2 by 2 very simple covariance matrix. And what I'm plotting is the surface of the objective. And what you can see is it's maximized along the x is equal to y direction. That's the principal eigenvector, minimized along x is equal to minus y direction. That's basically the smallest second eigenvalue. Okay, so, oops, sorry. So what we are going to focus on, so there's something on chat. Okay. So what we are going to focus on is, let me move the chat here, a stochastic gradient type algorithm where I see one data point at a time and I make an update. Okay. And finally, at the end of seeing n data points, we hope that we have a vector which is close in a suitably defined sense, and I'll get to that in a second, to the principal eigenvector of the unknown covariance matrix. So the SGD update is very simple. You just take the gradient, right? This xt transpose wt times xt, that's essentially the gradient. You multiply it with some sort of a step size, that's your gamma t. And you keep updating your weight vector. Okay? The only issue with this is, well, I do have the norm constraint. So all you do is you project it down on the unit sphere. And that's it, very simple. How do you initialize? You just pick a unit vector uniformly distributed on the d-dimensional sphere. Okay. So I hope that algorithm is clear to everyone. Again, it's really just a projected gradient descent algorithm. Okay. So now it turns out it's a very old algorithm, even though, you know, SGD has become like the modern workhorse of all deep learning big data problems. This one goes back to Eric Kioya, who introduced it in 1982. Many of you may know him for his seminal work, not just for streaming PCA, but also independent components analysis. And this update, in fact, has roots even going back in Hebbian theory, which was introduced by a psychologist, Donald Hebb, in his 1949 book. And basically has this very simple model of a neuron, like a one-layer linear neural network, one node, in fact. And it turns out when he suggested this, and it kind of didn't work because he was missing the normalization step. And that's kind of what we are doing. We are taking a gradient, but then we are projecting it back on the unit sphere. That makes things stable, and under suitable conditions, things should work. Okay. Right. So the nice thing here is typically in PCA, if you are doing it kind of an offline batch way, you will calculate the sample covariance matrix, right? And that's going to take a d by d space or d square bits. If d is very large, you don't want to store such a huge matrix. And this algorithm, the stochastic gradient algorithm, is essentially allowing you to calculate or estimate that vector, principal eigenvector of sigma, without actually having to calculate or estimate the covariance matrix explicitly. Now, the step size can be set as either in an adaptive fashion, it goes down as 1 over t, or it can be something like just a fixed log n over n, where n is the number of data points. Okay. So what we are going to do is we will just set our step size as something like eta n over n. Eta n is a very slowly growing function of n. It's enough to just set it as log n. Okay? Now, if you kind of write down the updates of Oya's algorithm, the final vector, if you sort of unwind it, ends up having this form. Sort of, it looks a little complicated, but let me tell you what's happening. In the numerator, what I have is product of n independent matrices. Each one of them is I plus a rank 1 update of the identity matrix. So I is the identity matrix. And once you have that product of n independent matrices, you are multiplying it with U0. U0, remember, is your initial vector, which is, you're going to just take it uniformly distributed on the unit sphere. And then you are normalizing it. That's the denominator, that's the norm. The question is, why would this algorithm work? Okay, so let's kind of build a little bit of intuition there. So if I just was being really hand wavy, and just for the sake of building intuition, let's look at the numerator, forget the denominator is there. Let's just look at the numerator. In fact, let's take expectation of that numerator, even more hand wavy. Right, so what's going to happen is that expectation, everything is independent, so the expectation acts on each one of those things. There are n matrices in that product. I go take an expectation of each one of them. All of them are identically distributed, so I end up having I plus eta over n times sigma whole to the power n, and then multiplying by U0. So essentially, it's like a matrix exponential, right? And if you look at the eigenvalues of that matrix, what's happening is, excuse me, it's taking all the eigenvalues of sigma and it's just exponentiating it. They're all getting mapped to e to the power eta n times lambda I. So if your eta n was log n, then it's from lambda 1, you went to n to the power lambda 1, from lambda 2, n to the power lambda 2, and so on and so forth. So what it's doing is it's amplifying the gap between the eigenvalues. And when you take inner product or you just project it down on U0, it will pick out the component corresponding to the principal eigenvector, because that's the dominating, that has a dominating eigenvalue. So there has been a huge amount of work in computer science, electrical engineering on Oya's algorithm. And but before I kind of give you one of those versions, I would like to do a little bit of notation. Remember, sigma is the covariance matrix. V1 is the principal eigenvector. Lambda 1 and lambda 2 are the top two eigenvalues. So for this talk, we are just focusing on the principal eigenvector, and that's the gap between the largest eigenvalue and the second largest eigenvalue. So the way we will measure Oya's algorithm, and that has been traditionally measured, is by looking at the sine squared error. So V Oja is essentially the vector you are getting after your n updates. This is your estimate. You take an inner product with V1. Remember, V1 is our target vector. We want to estimate that. So the square of the inner product is going to be the cosine square, and you are subtracting it from 1. So it's essentially giving you a sine squared error. Now, out of the many papers, and several are even like, if you maybe look at like the last 2 years, there has been papers on analyzing Oya's algorithm in different settings. So the one I would like to talk about gives you a very sharp rate, and it matches the error of offline calculation of principal eigenvector up to logarithmic factors. Okay, so this was done by Jain et al. In 2016. Now here is a very strong condition that if I look at the outer product of x1, x1 transpose, x1 is my first data point, it's a d-dimensional vector, minus its expectation, and take the operator norm, this has to be bounded almost surely. And I want to point out that this is something that shows up nearly in every paper, okay, on Oya's algorithm. And then you have some conditions on that gamma t, this is your learning rate. And finally, what you can show is that with probability at least 3/4, the sine squared error is going to go down as 1 over n. And of course, there are terms which are related to the eigengap. You have to have an eigengap and so on and so forth. So a lot of times, I get questions about, why does it have to be bounded almost surely? If it was a really high dimensional problem, right? Then the sample covariance matrix is not going to give you a good estimate. So what we are saying here is, even though it is high dimensional, hidden inside it, there is a low dimensional problem. And having the operator norm of that quantity to bounded almost surely essentially gives you that setting that, I am working on a sort of a lower dimensional problem, even though the data I'm seeing is in a high dimensional space. And it's kind of not something we can get away from, shows up in nearly all the papers that I have seen on Oya's algorithm analysis. Okay, so are there any questions?
Can I ask one quick question about this condition? This is Abhishek, actually.
Yeah, hi, sure.
Yeah, so the X1 transpose, that's just like a random vector, random matrix, right? Like for one realization of the X. So that's essentially a rank 1 matrix, right? So its maximum eigenvalue is essentially its trace, right? And that is basically X transposed X, and that would be of the order of D, right? I mean, so, and on the other hand, it's okay probably to assume that the maximum eigenvalue of sigma is order 1, like the population. So the difference between them seems to me to be of the order of D generally, right? Where D is the demand.
Yes.
Right.
That's a great question. Sorry, so you were asking that if that's what's going on, or?
Right. So if it's like, if you're going to talk about high dimensional settings, so this is never going to be bounded, correct? Because it's going to be of the order of D, right?
You are absolutely right. And in order for it to be bounded in a truly high dimensional setting, I'll have to have a low dimensional setting. D will have to be small or growing slowly with N.
All right. Okay.
Right. So in all of these cases, what you are really saying is you are absolutely right. The norm of X1, that is growing. We are going to say it's growing slowly with N, but the typical analysis says that the norm is essentially bounded, which is, and you will get that if you kind of had this sort of, like a decay of the eigenvalues of sigma, which is again saying that most of the action is happening on a lower dimensional subspace. So that's
so it probably impose some kind of structure in the correlation among the coordinates of X. It has to be.
Yes, correct. Exactly. Yes, yes, absolutely right. So that's kind of where it's hiding, that condition is essentially hiding the fact that we are dealing with a low dimensional problem, which is hidden in the vectors are super high dimensional, but there is a low dimensional problem.
Okay, all right. Thank you.
I had a quick question. This is Anirban. What kind of sigma matrices would satisfy this condition? So just following up on the previous question. So a spiked covariance model would certainly, but if it had small effective rank, would it still satisfy this?
So as long as you have the diagonal, like the variances are decaying, so the trace is not growing very quickly, that should be fine. But if it's not, if it's D, then it's never going to work. And I have some experiments later showing that if you don't have a strong decay, you are kind of like, can't really do anything.
Okay. Thank you.
Thank you for the questions. Now, so what we wanted to do is not just, so the error, the sine squared error and its analysis has been done. What we wanted to do was to do a distributional approximation of the sine squared error. That's what this talk will be about. In particular, what we will show is that, suitably weighted or not, well, a scaled sine squared error kind of behaves like a chi-square random variable under some conditions on sigma. And then we will say that, well, I don't know the parameters of that chi-square, so how am I going to estimate it? Well, we are going to propose a online multiplier bootstrap method to estimate that distribution. Okay, so that brings us to approximate the distributional approximation. Let me quickly see the time. Okay, so oops. So before going into the matrix case, what I would really like to do is just build intuition with scalars, right? Because then, remember, I have a product of independent matrices. Matrices don't typically, in general, they don't commute, but scalars, they do. So let's see if we can get something out of just pretending everything is a scalar. So Xi's are numbers. And what I have is, instead of looking at I plus gamma times xi transpose, I'm now looking at 1 plus 1 over n. That's I'm just setting my learning rate to be that times xi square, and that's my product. And I'm subtracting off the expectation of that. Now, if you write that whole thing out, okay, and it's not very nice, but you can expand it out easily. You are going to have these terms. So let's look at the very first term. The very first term is essentially an average, like some scalar thing times an average of mean zero random variables, independent mean zero random variables. The second one is a product of pairs of mean zero random variables and an average of that. And third one is triple, and so on and so forth. Now, this is very reminiscent of the Hovding decomposition of U statistics. So it's almost like, I've taken that quantity and now I'm just successively projecting it down on the linear space of random variables. So the very first term is giving me, after I've taken the expectation out, is basically giving me the height projection. The second one is pairs of random variables. Third one is triples of random variables. And the nice thing about this is, just like Hovding decomposition, each one of those sums, even though it's like, if I look at the second sum here, it's a sum over n square things, but they're all uncorrelated. Okay? Same thing for the n cube and n to the power 4 and so on, the successive terms, they're all sums of uncorrelated random variables. And furthermore, they are also uncorrelated with each other. Okay? And that's kind of the structure that also pops out of the matrix case, as I'll show you later. Okay. Now, and this is exactly what I was saying. So the first term is essentially of the form summation I, some function of xi. And the hope is that this converges to a normal distribution. Okay. And all the rest of the stuff, we'll just try to bound it to say that they're very small. And the fact that they're uncorrelated is going to be key in bounding the error of the remainder terms. So now let's come back to the matrix case. Okay, so I'm going to call Bn the matrix product, and we can do a similar Hovding decomposition here. So the very first term, let's call it T0. It's the expectation, and it's kind of what I showed you in the very beginning. It's identity plus eta over n times sigma to the power n. Essentially, looks like this. So each one of those blue squares are I plus eta over n sigma. And I'm just multiplying all of them. So it's the same everywhere, so to the power n. Okay, so that's my first term. My second term is, so this one is, let me not call it the first term, like the 0th term, right? It's the expectation. The first term is the Hayek projection. So now you are just projecting on the linear space of the xi's. Okay, so this happens to be each one of these terms in that summation. The summation I know looks not very pleasant, so I kind of have this schematic picture so that it becomes clear in our minds what it is, what does that quantity really look like or stand for. So what's happening here? What is happening here is I have again a product of n matrices, and all that's the Hayek projection is doing is it's replacing the ith matrix in that, you saw this one before, it was just a product of n constant matrices. And in the Hayek projection, all that's changing is I'm changing the first, the second, the third. I'm swapping out the constant matrix by this, eta over n xi transpose minus sigma matrix. That's it. So now again, what I have is n terms which are being summed, and they don't, things don't commute, sure, but there is still some structure. So it's still eta n times the average of independent mean zero matrices. They're not identically distributed anymore. Okay, so that's great. Turns out that I typically have slides for T2 and T3, but I don't want to get into that. you can imagine that if you look at kind of the second term and the third term, you're going to have pairs of matrices and triples of matrices and so on and so forth. It's not very pretty to look at. But the same idea that, things are uncorrelated goes through even in the matrix case. Okay. So now let's look at how am I going to use any of this to calculate my sine-squared error. Sorry about that. So Bn is this matrix, giant matrix product. Okay. Turns out that the sine-squared error essentially involves the norm of this quantity. I have Bn, I'm multiplying with U0, that's my initial vector, and then I'm left multiplying with essentially an eigenspace of sigma that is orthogonal to V1, the principal eigen vector. And this is very well known. This is kind of the first step of any analysis of Oyer's algorithm. So from the matrices now we are coming down to a scalar quantity thanks to the sine-squared error, right? So what we will do is we'll first say that, we'll first show that if I write U0 as a linear combination of, its projection in the direction of V1, V2, V3, etc., where V1, V2, V3 are the eigenvectors of sigma, then the first direction, the projection on the first direction dominates. So that's step one. So what you have here is this U0 transpose V1 is the projection on the first eigenvector. And what is remaining after that is you have replaced U0 by V1. Okay, and we just basically, if we can show this, and which we do, and I won't get into the details, then it boils down to just working with U times Bn times V1, a norm of that vector. Okay. Now you go and do your Hovding decomposition. You say that, oh, okay, so I have U matrix on the left-hand side, a V1 on the right-hand side, and I'm going to just expand out Bn. Very first term is T0. Now remember, your U and V1 are orthogonal, and so the first term is going to become 0. And then the second term, third term, and so on. The second term is basically the Hayek projection. And we show that everything after that Hayek projection will have small norm. And this is all thanks to this beautiful structure that comes out of the Hovding decomposition, which is that, the fact that the summons are uncorrelated. And once you have that, all that is remaining is, oh, I have my sine-squared error, and that sine-squared error is essentially just norm square of a normal vector, because the Hayek projection, remember, is essentially an average of mean 0 independent random vectors. Okay, so if we can show that the Hayek projection, if we can show distributional convergence of that, then we are pretty much done with the first part. And that the sine-squared error suitably normalized or suitably scaled behaves like the norm squared of a normal vector plus small errors. Okay. So are there questions up until this point? Okay, so let me kind of tell you a little bit and talk a little bit about related work. There's a huge amount of related work on high-dimensional CLTs. The groundbreaking work of Chernozhukov et al. From 2013, and then Gaussian approximations of the maximum of high-dimensional sums and so on. In particular, what we will do is we will kind of adapt a proof by Zhu et al., which will help us to show that the Hayek projection indeed will have, it can be approximated by a Gaussian vector. So once that is done, this is our theorem 1. And again, I've abstracted it out a lot so that it's easier to talk about this. So let's say that U0 is drawn from the uniform distribution or d-dimensional sphere. Let's also assume that the largest eigenvalue is order 1. Now, if for a large, broad range of that eta n, remember that our learning rate is eta over n. I'm basically giving you a range for that eta. So it just has to be slowly growing with n. Now, we don't have conditions like x1 transpose minus sigma, the operator norm, has to be bounded almost surely. But we do need that the moments of some random quantities involving xi will have to grow slowly with n. So this kind of this low dimensional, this implicitly low dimensional problem in a high dimensional setting is very much there. And it's not something we can get out of. So finally, if these conditions are satisfied, then what we are showing is, if I look at the sine squared error of your Roja vector after you have seen n data points, scale it appropriately. And if you look at the CDF of that and do the soup error between the CDF of Z transpose Z, where Z is essentially a d-dimensional vector, d-dimensional Gaussian, which has to be suitably defined so that the covariances match up. And I don't want to go into very much of the details. Then the soup error is going to go to 0. So this is the first result, which is showing that sort of the sine squared error is behaving like kind of like a chi-square variable. And it actually matches, so kind of it matches with previous work in the sense that the error is 1 over n. So let me talk about that a little bit. Kind of what are the take-home messages of that theorem 1. The dimensionality can grow up to e to the power n to the power 1/3. So you can have very high dimensions, which is what Oya's algorithm is kind of useful for. The theorem does hold for a very large range of eta. You don't, so it's basically saying that I don't have to tweak a lot to get the right learning rate. And like I said, I basically need conditions on higher moments of this quantity and not an almost sure bound. And this is, again, satisfied under appropriate conditions on variance decay. And we had this conversation before when I was showing you that condition. So that has to be there, some form of variance decay. And finally, if we just translate our convergence result into an error bound, like, forget about the distributional convergence. Can I go back and get the rates that people have had, the sharp rates? It actually does match Jane et al.'s rates up to some logarithmic factors. Okay, so that kind of takes care of the first 2 parts, and I'm going to move on to the third one. But if there are questions, very happy to answer them. Or okay, I typically have this slide when I'm giving the talk to more of the computer science engineering audience, but I thought I'll still have it. It kind of helps to show what is typically done in Bootstrap and what it is that we are trying to do. There's a subtle difference. So anyways, Bootstrap, of course, is a celebrated method of estimating uncertainty. So there, what we are interested in is, there is some underlying parameter of the data, and I'm using some statistic to estimate that parameter. How do I get the variability of that, right? This is Efron's work from late 1970s. And traditionally, this is what we think about Bootstrap, right? I am given a data set. I'm going to create B Bootstrap replicates. Each one of them are basically drawn with replacement samples. From each one of them, I calculate my estimate. Okay, those are the stars. And from there, I have some sort of a distribution. Okay, and that the hope is that the variability there, sorry. The variability there is kind of going to, it's close to the variability we'll have if you could actually sample from that underlying distribution many times, if you had that mechanism, but you don't, so you can just go and do Bootstrap. There are many other ways of perturbing the data. We don't always have to do a with replacement sample. We can do Poisson sampling. There is multiplier Bootstrap, and that's kind of what we will focus on. But before jumping into our algorithm, I would like to kind of point out the 2 key differences between what we are more used to seeing for bootstrap consistency and what we will do. So in bootstrap consistency, what we do is we want to estimate the true CDF of theta hat. Okay, so probability that theta hat minus theta, this is the true hidden parameter smaller than t. And we are going to say that the bootstrap CDF is close to this. And the bootstrap CDF, all that's happening is you are doing a plugin, right? So you are saying, I don't know theta, so I'm just going to plug in by theta hat. And in the bootstrap world, my theta hat gets replaced by theta star. And this probability is going to be conditioned on data. So that whole error is a random quantity, and that converges to 0 in probability. So that's kind of what we typically see in the bootstrap world, or kind of, in our case, it's slightly different. In our problem, our theta n hat is now actually an estimate of the error for streaming PCA. So here is how it's different. And I have kind of like color coded them just so that you can compare. So for the true CDF, what we have is a scaled sine squared error between the OJA vector and the true V1 vector. Okay, and the red is the bootstrapped version of it. And the bootstrapped version is saying that condition on all my data points, if I now replace the V1, because I don't get to see V1, right? I don't know sigma. So I replace V1 by the OJA vector. And basically now I'm going to create these bootstrap replicates of the OJA vector. That's my V star. And that's going to give me some distribution. Okay, those two distributions should be close. So it's slightly different because I don't really have kind of in the traditional sense, here is theta that I'm trying to estimate, here is theta hat. So I just wanted to make that clear. And we want to show, of course, that this is going to 0 in probability. The key is to do this in an online fashion, because remember, it's a streaming algorithm. I get one data point at a time, and I want to keep kind of a running estimate of my OYA, or estimate of the V1, the principal eigenvector of the sigma matrix. So just as a schematic, here is sort of what we are aiming for. Okay, so you get a vector xt, it's a d-dimensional vector. You want to maintain a OJA vector that you would have done anyway, but that's your UT. And you are going to use some multiplier random variables, which are scalar variables, B of them. So, Z1 to ZB at the tth time step. Using that, you are maintaining sort of a bootstrap replicate pool, or which is just perturbations of that OJA estimate. So now the left-hand side is essentially the plugin for the population eigenvector, which we don't know, and the right-hand side is kind of the VOYA. Okay, so we are going to do inner product square 1 minus, so sine squared error between the OJA vector and each one of your bootstrap replicates. That's going to give you B numbers, and you can look at kind of the distribution of them, and we are trying to make sense of that distribution. Now, so how do we do this in an online fashion? And again, let's go back to the scalar case. Remember that in the scalar case, xt transpose became xt square. My gamma t was just 1 over, we just fixed it as 1 over n. Everything is just a number right now. Okay? So the natural thing that first comes to mind is to say that, well, before it was 1 plus 1 over n xt squared, just perturb that by throwing in a multiplier random variable, which is a normal 1, 1. So it sort of has the same mean as before, and hopefully that should work. And you just, that superscript I, just, change that I, like have I is equal to 1 to B. So that gives you your B replicates. And that seems like should be fine. Now, if you look at the Hayek projection, now the Hayek projection is going to be conditioned on the data, because in the bootstrap world, everything's conditioned on the data, right? So if we compare these two things, what happens, what you will see is one of them, the variance is off. Okay, so my multiplier, well, my candidate update or bootstrap perturbation, if I calculate the variance of that, it's going to have this extra sigma to the power 4 there, which was not there in the beginning. So something is off. That's not quite, even though it seems natural, it's not quite the right thing to do. So the right thing to do would be what we do in multiplier bootstrap, which is, well, sigma square is my mean of xt square. So I take that out, I center around that, and whatever is the noise, the xt square minus sigma square part, you multiply that with a normal 0, 1 random variable. Now that one has everything matches and doesn't have this like problem that I mentioned before. So let's now go from there and come out up in the matrix world and say that, okay, so what's the matrix equivalent of that? Excuse me. The matrix version of that is going to be sigma square gets replaced by sigma. And instead of xt square minus sigma square, you have again xt transpose minus sigma. And this is not a good solution because it assumes that we know sigma. And if you are thinking that, oh, maybe we can just estimate sigma by a sample covariance matrix, remember that the whole point of doing Oya's algorithm that I don't want to calculate a sample covariance matrix, and it'll be a very large D by D matrix, and we don't want to do that. Okay, so instead we do this fix. Okay, so what we do is we replace that sigma by another data point. So it gives me this particular update where we are saying that, oh, just treat sigma as something like xt transpose, and your new data point is xt minus 1 transpose. Okay, and you can switch the order. It doesn't really matter. The analysis will go through. So of course, there is this additional square root 2 factor there, because the moment you are doing xt transpose minus xt minus 1 transpose, that just makes your variance go up by a factor of 2. So that's why there is a correction. So now what we have done is everything is online. I just, instead of looking at one data point, I'm looking at 2 data points. And I think it's possible, in fact, to do that as a, like, look at k data points in the past too. But the analysis was complicated as even by this. So we just stuck with this. Okay, so now the trouble is there is a difference between what I showed you before, where we're not doing bootstrap. Now all of a sudden there is slight weak dependence between the XTs, right? Because I'm kind of like having 2 data points in any one. Every matrix in that product is going to have sort of 2 data points. But turns out that this is actually a pretty weak dependence as long as you condition on this event. So you basically say that, I'm going to work on this good set where the norms are again not growing very quickly with n. Okay, so again brings us back to this original assumption of the fact that my xt transpose minus sigma operator norm of that, it can't grow very quickly and things won't work. So this is basically, we are seeing exactly that condition even for bootstrap consistency. So here is our final online bootstrap algorithm. And so I get my data points. I have estimate of my OJA vector, which I'll use as a plugin of my population V1, which I don't get to see. And at every step, I'm basically going to use B multiplier random variables, which are all basically standard normals, to maintain B perturbations of the OJA vector. And at the end, once you have seen all n data points, you do sign squared error of the OJA vector that you have been calculating with all of your bootstrap replicates. That gives you B numbers. Okay, and then you just look at the variance of that or the distribution of that. And you have to scale it by some suitably. This n over eta n is essentially the scaling. Because remember that the sine squared error behaves as 1 over n. So I have to scale it up to do distributional convergence. Okay, so and this is bootstrap consistency. It's basically saying that, again, you know, like as long as this, with high probability, I have that the norms are not growing very quickly, then what I showed you before, kind of the bootstrap distribution and the true distribution, the difference between that condition on the data goes to 0 in probability. So we have this additional in probability. Okay. And again, when will this be true? Well, under appropriate variance decay, the alpha n will grow slowly. Alpha n is kind of being the upper bound on the norm. Okay, so I think I'm nearly near time. So, you know, there are lots of questions here. This OYA type update that I just showed you, they are everywhere in machine learning. You see them in subspace tracking, matrix completion, and so on and so forth. I only showed you IID streams. Something I'm working on right now is if I have weakly dependent streams, does similar results hold? I'm just showing you one eigenvector. What happens if I want to look at top k eigenvectors, and so on and so forth. I'm going to show very quickly some experiments, and they're really just a sanity check or proof of concept. So what I've done here is I'm generating d-dimensional uniform random variables such that the covariance matrix again has this variance decay. So there's a lot of sentences here. The only thing I want you to look at is that beta. The sigma I is the beta is large, you have a quick decay. If the beta is small, then you have a small decay. Okay, so so once you have that, what I'm going to show you, let me just quickly go here, are two plots. Well, two sets of two plots. The first one is when beta is equal to 1. So I have quite a bit of variance decay. The left plot is n is 1000 and d is 500. Okay? And the right one is I hold the d same, but I increase my n. And you can sort of see that, well, and the red and the blue are the bootstrap. So the red is the true CDF, the true sampling CDF, and blue is the bootstrap CDF. And you should kind of look at the difference between the two. And what this is saying is, sorry. If I increase, you know, if I have a lot of data points thrown, and the problem, of course, the gap is going to get smaller and smaller. It is not surprising at all. So the thing that I want to show you is when it doesn't work, and it's this case where beta is 0.2. So you are basically saying that, you know, the variance decay is very flat. And again, same setting, you know, like the gap between n and d is small, the gap between n and d is big on the right-hand side. And again, the two CDFs, the colors are the same. And what you can see here are the two things that they're very clearly different. And the other thing is, look at the x-axis. In the former plot, the x-axis, the numbers are small. Okay? Because, you know, when you multiply by, you are looking at n times the sine squared error. If there is distributional convergence, that should sort of stabilize and not blow up. And you can see here, those numbers are really large. So that's kind of the convergence is not really happening. And of course, if you give it a lot of data, maybe it will happen. So it will kind of get a little better, but sort of telling us that we can't really do away with those assumptions. And that's it. Thank you.
Thank you so much, Purna, for the very nice talk. We are all clapping virtually, trust us. Okay, so I'm going to open this up to the audience now for questions. If you have any questions, please go ahead and unmute yourself and ask your question.
Can I ask a question, please?
Yeah, go ahead.
It's a really nice talk. So I have a very strange question. What does online high dimension mean? Because like as you go do something online, you're getting more and more data points, but your dimension is kind of fixed. And so the idea about online is that sort of your data is coming so fast, you have to find a quick algorithm to do the estimation. But in my head is hurting trying to figure out kind of how the asymptotic, what it means asymptotically, because in the end, your sample size is going to catch up with your dimension.
Yeah, no, that's actually a great question. So, so typically, when you see kind of the analysis of Oya's algorithm, you always say that my D is fixed, my N is going to infinity, but at what rate? Or, you know, how many, I mean, do I need, if my, let's say that you are allowed 1 million data points, then how big a dimension can you kind of tolerate? I think that's how I will think about it, rather than thinking about this as, you know, the dimension is fixed and I can just get as many data points as possible. So eventually, you know, if I have 1 billion, D is equal to 1 billion, I can have 5 billion or like, you know, like billion square data points. So I think that's kind of how I will think about it, not as, you know, like D is growing with N. Does that make sense? So more of a, you know, if I am allowed some, maybe I'm allowed 5 million data points, okay? And let's say my D is 1 billion. Can I actually get something from those 5 million data points for that billion dimensional problem?
Okay, thank you.
Yeah, that was a great question. Yeah, thanks.
Are there any other questions for Purna?
I have a question. So, first of all, very nice talk. And my question is regarding the variance decay, and it is connection. It is related to Anirban's question. So, suppose like I have a single spike model sigma. So it is of the form identity plus say lambda VV transpose. So then in that case, like the variances are just going to be 1 plus lambda VI square. And from your simulation, it seemed to me that your assumption will hold if the VI, so these are just the elements of the, like the largest eigenvector, they decay exponentially. Am I correct, or do you need some more stronger assumption?
So let me think. So if it is I plus lambda VV transpose, sorry, I'm thinking right now.
And V is just a vector.
V is just a vector. Right. So I would need in that case either your V is sparse, right, or kind of like the norms of it are going down.
Right. So you need either V to be exactly sparse or the VI squared, they are going down. So now if it is sparse, then I am wondering like your assumption, like how does it equal to kind of like the sparsity, the bound on sparsity? Because what I was kind of thinking is you have this lower bound results on high dimensional PCA that if your sparsity is greater than n by log P, then recovery of the largest PC becomes information theoretically impossible. So yeah, like is there a mapping between your condition and the sparsity? So that's
actually, I haven't thought about it. Thank you for bringing it up, and I'd like to think more. I don't. That's a very nice question, but we have not looked at that. Yeah.
Okay. Yeah. Thank you for.
No. Thank you for the question.
Can I ask a quick question too?
Yeah, please.
So throughout, one critical component was that little eta n thing, which you need to be slowly or slowest of all, but diverging, right? So one way or the other, that ultimately affects your rate, right? It's just makes it slower than the parametric rate, right? Eta n over n, because it's the squared quantity. So the parametric rate is 1 over n, right? So do you really need the eta n to have to be slowly like diverging, or can you set it to be like some constant order? How critical is it? I saw the condition that you need it to diverge there. I'm just trying to understand why.
Right. So I think you do need a log n. So let me actually go back to the very first, sorry. Just clicking in. So give me a sec. Let me show you the very, yeah, right here. So you see the eta n. So when you are doing that exponentiation,
Yeah.
what's happening is the eigenvalues are becoming e to the power eta n lambda I.
Right.
If eta n is at least log n, then I do get the n to the power lambda. So that's where the eta n having being at least log n comes in.
I see. So you cannot just set it to be like constant, like 2, 3. That's not going to help. It's going to be set as log n.
Yeah, and typically, if you sort of if you look at what people do with adaptive rates, they don't do eta n over n, right? They basically say that eta, so gamma t is 1 over t, and then also kind of the sum will be something like it'll be something like a log n, and that log n will help. And that's, yeah, it would be interesting to see what happens if I just make it a constant. I'm not sure, but the analysis, I think here is where it will.
Right. And another sort of different question maybe has some connections to Nilanjana or Anirban's question before. So I'm trying to understand again the behavior of that alpha n quantity, the upper bound on the L2 norm of your xi's, right? So if your xi, so this is, let's just say we have a single random vector here. So if your xi's are fully kind of independent components, right? And let's say they are all just Gaussians or sub-Gaussians or something like that, right? So then that's, then that is again that rate alpha n is going to behave polynomially in the dimension, correct? And because if they're all sort of independent components. On the other hand, so let's say they're all sub-Gaussian sigma square or something like that, right? Independent sub-Gaussians. On the other hand, if they're all, let's look at the other extreme, that they're all perfectly dependent, right? They're all the same x1. Every component is the same guy. So then again, it's again going to involve a d. So the difference is between d and root d, from extreme independence to extreme dependence. So I'm trying to see where you can hit a sweet spot, if at all, where the alpha n will not polynomially depend on the dimension, right? And maybe this is something, may have some connection to some sparsity conditions that you were mentioning before, right? I don't know if you have any thoughts on this. This is a kind of an open-ended question. So
I know. So when you said x1, you are not talking about like the data points. You are looking at entries.
At a single vector, all entries to be the same variable. So that would be extreme dependence, right? Right. So that would be, but because you're considering the whole norm, like the L2 norm, so they will still get added up, right? On the other hand, if you're talking extreme independence, that all coordinates are independent, and let's say they're sub-Gaussians, right? And the sub-Gaussian parameter is some, of course, like some constant, right? Sigma square or something. Again, the sub-Gaussian parameter will add up to give you an order of d, correct? The overall parameter, overall behavior of the norm. So I see both extremes depending polynomially on the dimension. That's why I was wondering.
Yeah, I mean, I feel like, okay, so the question, I think by Nilanjana, if I'm not wrong, was about sparsity. And I feel like that is definitely something that I want to be looking at, kind of what is the connection? And if I really said that, hey, I have sparse things, and here is sort of the lower bound on sparsity or upper bound on sparsity. We didn't go that route, right? We just gave a bound. The other end of, if I'm understanding you right, sort of, if I actually have a high dimensional problem and somewhere between your two regimes, I have a feeling that you would need a different kind of algorithm there. So something like Oya's algorithm, but perhaps with some sort of thresholding or pruning or regularization. And I think that's a very good question. And I don't know right now.
I see. Okay. All right. Thank you. Yeah. Are there any other questions for Purna at this point?
I have a quick question. Thank you
go ahead.
for the nice talk, Purna. So Just so a question you try to do an analysis for, let's say, a different metric, let's say something that measures entry-wise error or things like that. Do you think this is still possible to extend to those type of things? Let's say you want to measure entry-wise error or use Bootstrap for estimating the entry-wise error of the OJS eigenvector.
Oh, sorry, sir. So sorry. Will you repeat your question?
So,
I
I guess my question is whether you think it's possible to extend these ideas or to apply these ideas for other types of errors, let's say entry-wise errors, or instead of the sine theta distance.
That's a great question. That's what I'm trying to do right now. So instead of doing a sine squared error, can I actually give entry-wise error? And I've never seen anyone, it's not done. I haven't seen this. That's what I mean. Maybe I'm wrong, but yes, and I think it can be, because you can look at those like high projection vectors, and instead of looking at norm of them, you can actually look at sort of, max of them. And that's something I'm looking at right now. I think that will be really nice. So yes, thank you for that question. Yes, I think it should be. We should be able to extend it.
Okay, thank you.
Okay. Great. Are there any other questions at this point? Well, if not, let's thank Purna virtually again for the nice talk